him, what he's done is he's synchronized all those thoughts. But he's at rest in the car. He could get out of the car, walk around, everything perfectly normal. Well, I don't know how easy you can get out at 97 feel like, but if he just looks around his car and he sees everything's normal, everything's at rest, right? And he synchronizes all these thoughts all the time, right? And then this car whips by somebody, and they take a snapshot of this car. They will see all of these thoughts at different times. So you will see, so what do you see? Well, I'll let you think about it. You'll either see this clock ahead, a back clock, or behind, right in front of it. So you're sort of seeing the car at, okay, let's suppose that it's Bob who's moving like this. Really fast. Then it's sort of like you're seeing Bob sort of tilted in time. Okay, you're seeing, let's suppose it's future here and then past here. Okay, you're sort of seeing Bob's head, say, 5 years later than his feet. Okay, so his feet, they're a little like baby feet, and he has a little man hair. So it's like that. That's exactly right. Okay, so yeah, it's really, it's sort of like it's really this. Remember that picture there with all these lights. Okay, any object occupies not only space but also time, also exists in time. So here's an object. This box, it occupies some volume of space. But as time goes on, it continues to occupy that volume. So t equals 0 is there, t equals 1 is there, in fact it's there for all time continuously. Okay, so an object, any object occupies actually a four-dimensional volume of space-time. Okay, the ordinary three-dimensional volume plus it's sitting there for all time. So this is my object at going from there to there on the x-axis at t equals 0, goes from there to there on the x-axis at t equals 1, and so on. Okay, but this is true for all times, and so it's actually a continuous, it's a full solid. Okay, so any object occupies a four-dimensional volume in space-time. Okay, so that's what that object looks like. This is what that object looks like to me when I'm at rest in again, or is at rest in me because it's not moving in space. If someone is walking by that object like this and looking at it, measuring its length, looking at clocks all over it, so on and so forth, what they are seeing is that's their time axis, that's their space axis. What they're doing is they're seeing different cross sections of it. Okay, so what I see are the horizontal cross sections of this. When my clock reads 0, I see that cross section. When my clock reads 1, I see that cross section. So I'm seeing different cross sections of this four-dimensional object as time goes on. Bob time, or those Bob, the script of whatever, just all the Bobs along, Bob time, Bob double time along, that. They see different cross sections. They see that cross section. At a later time, they see that cross section, then that cross section. Okay, so it's a four-dimensional object, you're just slicing it up differently. Okay, so Alice Prime say, yeah, okay, I see loads of points of time on these. Bob Prime, they're looking at a point of the object, but on the right-hand side of the object, the point they're looking at is actually in the future of the point on the left-hand side, according to Alice Prime. It's just different slices of the same four-dimensional object. Right, okay, so what I want to focus on right now is something that we talked about near the beginning, which is understanding principle P2 prime. Does anybody remember what P2 prime is saying? Yes, with observer and switch folks. Okay, so principle P2 prime is that a principle is a concept of object light, but the one that Einstein did not say. Okay, it's the one that says something really bizarre, which is if I have a source at rest there, flashlight shining light towards me, I'm at rest, which is sure I never see. But this principle here, P2 prime says that not only will I never see under those circumstances, but if I run toward that light, I will also never see. If I run away from it, I will also never see. That's completely incomprehensible. It doesn't make any sense at all. If light is a wave, there's no way. This wave is moving at some speed c, at 5 meters per second, this way. If I'm moving toward it, I'm going to measure a faster speed. If I'm running away from it, I'm going to measure a slower speed. If light is a particle, if it's firing off particles like this, little particles are flying through space like this at some rate. If I'm not running toward those particles, they're going to be coming at me faster. There's no way this makes sense. Either a wave picture of light, a particle picture of light, no picture of light, for which this could make sense. And yet, as I ask you to think about it, this is actually a logical consequence of P1 and P2, the unbelievable principles. Okay, so how is it possible? Well, it required a new understanding of space and time. In particular, it required the realization that simultaneous for me is not simultaneous for everyone. Okay, so let's look at that. Okay, so we'll take the simplest case first, which is I got a flashlight at rest over there, and a flashlight at rest over here, and I'm going to measure the speed of light, and I'm at rest with respect to those flashlights. Okay, so that's the first case. Okay, so let's sketch the picture first, and then talk about it. Okay, so there's Bob at rest. There's Bob's time at rest. Okay, and they have and there's a platform connecting between them, a stoplight belt. Okay, and then let's sketch this part of it. So these are like these. Yeah. All these fundamentals are speed times time. So this is Alice. Okay, so there's something going on in Alice's space and time here. In Alice's space and time, what's going on is very simple. Bob is standing over here at rest, and Bob Kahn is standing over here at rest next to her, some distance L away. Okay, and we've got a flashlight over here, okay, which emits a pulse of light. Okay, at t equals 0, according to Alice's time over here, okay, this flashlight sends out a beam of light, pulse of light, which travels at 45 degrees, it's coming this way 45 degrees, speed of light is sent to Alice. Okay, and let's see. So what we know is because pulse of light starts over here, way over there, it drifts to the left, at the speed of light, right on the speed, we're going to measure that speed. Okay, then first it hits Bob time, and then it drifts across that platform, and then it hits Bob. Remember, this platform occupies this entire four-dimensional volume of space, right? So the platform at a later time, the slide you're looking at is this one here. Okay. So the pulse of light starts at one end and travels across to the other end. And because this is 45 degrees here, if that distance is L, what is that distance? And this is also L. Okay, remember, we're measuring this in meters and back in meters. Okay. So technically, what is this now? What is the difference between there and there? We better understand typically. Time to make the light to travel across the platform. Okay, actually it's 2 times. This TTD times, or C times, time it takes the light to travel across. That's C times the change in the radius of Bob. Okay. So if we were to measure the velocity according to Bob, well, that's the distance over time. The distance involved here is what? Now, we find out all this now. Now, delta TD. What is delta TD? L over C. This is TD over C. Okay, so let's just be like, same deal for a ray of light coming from the other side. Okay, so now we have a flashlight located over there. At t equals 0, according to Alice's law, this flashlight emits a pulse of light. It travels to the right. It first hits the left end of the platform, it drifts across the platform, hits the right end. And the time taken is this same deal looking across the sea. Okay, so that's trivial. Okay, now let's go on to the non-trivial case, which is what happens if Bob time are moving to the right. Okay, so they're running now toward the flashlight. They're running toward the flashlight. They're running toward that flashlight and away from that flashlight simultaneously. Okay, so we're going to actually go to version. Let's go. Let's wait for it. I actually don't. I'm going to suggest that. Okay. So this is Alice's space. Alice's time. But now Bob time are running toward that flashlight and away from that one. Meaning that they're drifting through Alice's space. Okay, so here we go. This is a bit trickier. This one here. Okay, so let's draw that one. And that one. Depends on the prime. Okay, and okay, let's just get this point here. Okay, so if this is Bob's time axis, where is his space axis? Same angle. Okay, so I go 45 degrees. Not 45 is this. Does it look like about the same angle? Okay, so let's try that. Okay, so that's the platform. And halfway between is speed of light. So that angle is the same as that angle. Okay, that's not strange. Okay, and let's see here. So let's start with this guy. I don't put 45 here. Okay, and another top here. Okay, so this is. Okay, so let's start. So there's our flashlight, and at t equals 0, same as before, at t equals 0 according to Alice's law. This flashlight is on. It sends a pulse of light moving through Alice's space at speed. It first hits Bob prime, the right hand of the platform. That platform occupies this entire volume of space time. It drifts across the platform, hits Bob at the left end of the platform, and back again. So we have the platform at 2 times, according to Bob prime. The first time is when the light beam hits the right end, and the second is when the light beam hits the left end. So this is the law later on, for the platform. Okay, and it joins up over here. Okay. So now let's see here. This angle is the same as this angle. What do you think about these two distances? This is 25 seconds, this is 45. Right? Okay, so basically, if Bob prime are using a meter stick, it will go zoom. We'll say, okay, the length of our platform is now 7 meters. Okay, we are plotting C times TD over here. Okay, so when we plot meters versus meters, then just because of the symmetry of this, you can see that this is also going to be L. We have now the time according to Bob. The last time between when this light pulse hits the right end, that's the end. At the right end of the platform is the same. That one just hit the right end. And so we're going to see it's simultaneous with that event. Okay, so Bob at this time says, hey, Bob prime, I noticed that the light beam hit your end here. Okay, my clock read this. So you know, Bob reads 3 seconds here, and Bob prime's clock also reads 10 goes simultaneous. Okay, and then that ray of light travels across that platform, and time, and meanwhile, time is ticking for Bob at the left end of the platform. And the number of seconds hit is this string L here, and then he receives the signal at this end of the platform. Okay, so what is the velocity that Bob sees? Well, the distance over time is where Bob time. What is the distance that the light ray travels? Just L, same as before. What is the time? The time delta T D is the same as before. Delta T. And that's C. Okay? And similarly, we could extend this ray of light here up to where it was here. Okay? And extend it down. Okay, so this is the flashlight, so now they're running. That's the flashlight located over there. They are running away from that flashlight. Okay, so this light beam is chasing after them. Okay, but since they're going at less than the speed of light, it will eventually catch up with them. It will get the left end of the platform here, and then it will continue on, and eventually hit the right end of the platform here. Okay? And so the distance to travel is the same thing now. The time it took is the distance from there to there. Okay, but the distance from there to there is the same distance from there to there. This is just it's just this square, which has been like squashed like this with my shape. Okay, so it's all symmetrical. So both of them either, if they're running toward the flashlight or away from the flashlight, will then have the same speed of light c. And this requires something very special about the nature of space and time. It requires that this time that the space axis tilts. Okay, there's a tilt in the space axis. You can see that if I didn't have a tilt in that space axis, I wouldn't have this nice symmetry. It would all just fall apart. This tilting of the space axis, this relativity of simultaneity, the fact that if those two events are simultaneous for blah, blah, time, like that, they're not simultaneously. They're not kind of crowds. This happens first and this. That tilt is required to explain how it is possible and completely natural running toward or away from the flashlight, even if it's the same speed. It requires a revision of our basic understanding of what space and time are. Okay, does that make sense? Excellent. How much time do we have? Understanding about special relativity and the nature of space and time to be able to do that. And this is a wonderful topic today called Einstein's rotating disk thought experiment. So some of you may know that Einstein was famous for his thought experiments, and this was a particularly important one, which played a significant role in him bridging the gap between special relativity and general relativity, putting him on the right road towards general relativity. So let's see how this works. Okay, so Einstein's rotating disk thought experiment. Okay, where's our word chunk? Okay, so here's the situation. So we got we're on a space station here, which is floating above the surface of the Earth. And inside we got Bob, and Bob is weightless, just like the astronauts in the space shuttle. Okay, so there he is, floating around weightless. Should we talk a little bit about weightlessness? You want to talk a little bit about weightlessness? Okay, just very quickly here. So this is a famous thought experiment much earlier by Newton, where he discovered a really clear way of thinking about how objects orbit around, say, the Earth. So, for example, the Moon, or in modern times, satellites and so on. Okay, so here we've got the Earth, and here we've got a tall mountain like this, and we're standing on top of this tall mountain, and we're going to can do that by just rotating the spaceship. Okay, so next up is the idea that we'll just forget about the Earth and all that stuff, and we'll just focus on Bob and the space station here, rotating space station, or spacecraft. So what we were talking about for the amusement ride is Bob basically lying on his back. He feels like he's being pressed against the wall. Okay, and he's looking around like this. Around and around. Okay, now, I want you to be convinced that Bob could also just stand up. Okay, so Bob could stand up so that the inner surface of that cylinder is now his floor. Okay, his arms would feel heavy, and they would drop down like this, and he would be able to work into the workstation and do stuff in his artificial gravitational field, and so now he's very happy. Okay, so how many of you are okay with that? Is that all right? Okay, so from Bob's point of view, he would consider this to be up. So the direction towards the central axis of the cylinder is up, and the direction towards the floor is down. Okay, so the gravitation, this artificial gravitational field, defines up and down for him, just like the real gravitational field on the Earth defines up and down for us. Okay, so we got that. So now the question we have is, we've got Bob in something which seems like a gravitational field, an artificial gravitational field, and the question is, how closely does that artificial gravitational field mimic the real gravitational field that would be produced by a mass, like the Earth or the Sun or a galaxy, that kind of thing. Okay, so how close is artificial to real? Okay? Alright, so whenever I say real gravity, I mean that gravity due to masses. Whenever I say artificial gravity, I mean that gravity due to motion. Okay, acceleration. Okay, so one experiment that we could do is Bob could hold onto an apple in his hand here. Okay, so what we're going to do is we're going to take a top-down view, looking down the axis of the cylinder and seeing Bob going around and around like this. Okay, we're going to analyze the situation of him holding onto that apple. Okay, so let's suppose that Bob is over here, and he's holding onto an apple like that. Okay, what's the motion of the apple? This side is sitting. The whole space station and Bob, who's holding onto the apple, are spinning around. Where's the motion of the apple? Right. So the shape of the orbit of the apple is moving in circular motion, uniform circular motion. Okay, so here's the apple. It's moving around in uniform circular motion. Okay, so what's required to put something in uniform circular motion when you get moving in uniform circular motion? Yeah, so uniform circular motion means there's an acceleration directed towards the center. So if there's an acceleration, there's a force. Okay, so in order for this apple to be moving in this uniform circular motion, requires that there be a force acting on that apple, and that force be directed towards the center. Okay, so there's a center-directed force. Where's that force coming from? Normal reaction? Yeah, so the parent, so Bob is exerting that force. That's where the force is coming from, right? So let's see if so here's the situation from Bob's point of view. What Bob notices is, I'm standing in this thing. I actually think I'm going to know that I'm rotating. Okay, I'm just standing inside this thing. It's a sealed container, a sealed cylinder. I don't have any windows to the outside. I can't see the distant stars like this. I can't see that rotating relative to the distant stars. I just feel this weird kind of artificial gravitational field. I realize I feel this artificial gravitational field. I'm hanging onto an apple like this in my hand, and I notice that in this state of whatever is happening, in this state, I feel like I'm pushing up on this apple. Okay, so I'm exerting an upward force on this apple. Okay, so that's exactly the same as Bob standing on the surface of the Earth. Okay, I'm standing on the surface of the Earth here and hold this piece of chalk. I'll have to keep pushing up on this piece of chalk. So I'm exerting this upward force. Okay, so far so good. So with this simple experiment, Bob wouldn't be able to distinguish between whether he's inside this rotating space station or whether he's on the surface of the Earth, for example. In both cases, it's phenomenologically the same. He's exerting an upward force. Okay, what if Bob releases the apple? What if Bob just drops it like this? What if he removes his hand? So this apple is whipping around, so Bob and the apple are whipping around and around and around and around like this. And then suddenly, at this instant of time over here, Bob releases the apple. What's going to happen to the trajectory of the apple? Okay, it's going to move exactly tangentially to the circle. So whatever the velocity the apple has, at the instant that Bob released it, it would maintain that velocity. There's now no more force acting, the acceleration stops, the velocity remains constant. It remains exactly what it was at the instant it was released. Okay, so what will happen is